Okay, well, like Edzard said, I'm Alex Cleveringa. I'm a PhD student, candidate, I guess, at Iowa State University with Dr. Fernando Miguez. And I met Edzard at the conference in Ames on statistics in agriculture, and he invited me to come here. So it's a pleasure to be here. I've really enjoyed it. Your campus is beautiful. We like to brag about ours, but yours is something special too, for sure. All right, the title of my talk is Losing Control, the effect of removing the control treatment in fertilizer rate trials. So hopefully we can see maybe by the title why I'm here. A little bit of background information about myself. I'm originally from Sioux City, Iowa, which is represented by that gold star there, right at the intersection of South Dakota, Nebraska, and Iowa. Now, if you're thinking Iowa, you're probably thinking something like this, stereotypical, um, you know, Iowa landscape. It's accurate. That's what Iowa looks like. Land use in Iowa looks like this. The brown color is row crops. The yellow color is hay and pasture. That's pretty much all of it. The red spots are cities. But we do a lot of agriculture in Iowa. We're also outnumbered by pigs in the state. They outnumber us 7-1. It's not even close. There are 24.6 million pigs and 3 million people in Iowa. And there are 3.6 million cattle, so they outnumber us as well. Iowa is 36 million acres large, and 30 of them are cropland. 13 million are corn, 10 million are soybeans last year. And the soils that we're working with, we've got alpha sols and mollisols. So pretty different from here. We've got high organic matter, clay content, a lot of loam, soil silt loams, and different things like that. A little bit about my educational background. I got my undergrad degree at Iowa State in agricultural biochemistry in 2015 and was a member of the marching band during my time there on the left. And I also was a member of the basketball pep band, third from your right there with the saxophone. Also during my time at Iowa State as an undergrad, I worked in a molecular genetics lab. And that was my first kind of exposure to grad school. And my response to that exposure was, I'm never going to do that. It seemed pretty miserable. They were working hard. They were losing hair, gaining weight, crying themselves to sleep. They told me all about it. And then they told me that I should do it. And I said, no. And here we are today. But anyway, so with this degree in agricultural biochemistry from Iowa State, I wasn't actually required to take any agriculture classes, and I didn't grow up on a farm. I didn't have any experience in agronomy. And so I was just at the career fair looking for a job my senior year. And in the fall, I was introduced to Corteva. They reached out, offered me a job. I accepted and then took 2 classes, freshman level classes in agronomy, so that I would know what I was doing at this new job. I worked there for a little bit, moved back to Ames, worked some jobs here, got married, and my wife said, oh, you should do grad school. I said, no, I shouldn't. I remember what the students said about it. And then a week later, she said, I think you should do grad school. Here's this program I found for you. I think you'd really like it. And so I said, great, I don't know how to get into grad school. I don't know what form I have to do, like forms you have to do. I think there's a test somewhere. And so she's like, well, you live in Ames, just go talk to your undergrad advisor. And so I did. And he's this really kind older gentleman. And he said, no, you just got to go talk to people. Now he's from a generation older than my dad's. And that sounds like my dad's advice. Just go talk to people. And I said, I don't think that's how it works. Like you fill out forms online. That's how you do it, right? He said, trust me, just go talk to people. So I walked next door and walked into the agronomy hall building and said, how do I get into grad school? And the woman I talked to said, I was just talking to a professor who's looking for a grad student. Let me connect you to him and we'll see what happens. And that was the beginning of August. And 2 weeks later, I was registering for classes on the first day of classes. I skipped the GRE exam for orientation. And that's how I found myself in grad school, where I got my master's degree in soil science in 2020. And during my time there, all the classes I took where it was master's and PhD students, I was like, man, these PhD students, they're on a different level than me. I could never get a PhD. One of the classes I took was crop modeling, and because I saw all these job offerings and emails that said, oh, there's a job in crop modeling here, there's a job in crop modeling here. I thought, I don't know what this is, but if there's jobs in it, I want to know what it is. And so I took a class on crop modeling, struggled my way through it, put together a presentation for the final project, and a couple semesters later, I woke up to an email from Fernando Miguez, who you might recognize from the first slide, inviting me over the summer at 6 o'clock in the morning to join his program as a graduate student. So that's how I got to where I am now. My degree is that I'm working towards is a crop production and physiology with a minor in statistics, and a graduate certificate, which is kind of a step below a minor, in food, energy, and water systems through the NSF. And now I just don't say anything, because if I say I'm not going to do something, I end up doing it. So I just keep my smart mouth shut. All right, some other projects that I've worked on. This on-farm nitrogen trials study, I'll just run through this briefly before we get into the topic we're all here today for. But it's a really neat tool, kind of shows summary statistics. It's interactive on a large data set for cornstalk nitrate data. We created a Shiny app in RStudio. If you follow the link, please wait till after the presentation is over. And here's the citation for the publication we got out of it. But here's just a couple screenshots briefly introducing what it is. So it's over 10,000 fields involved in this data set, and it covers a variety of states, mostly Minnesota, Iowa, Illinois, a little bit, Indiana, a little bit in Michigan and Ohio as well. And it shows the source of nitrogen. The summary statistics on the right are interactive, so as you zoom in and zoom out, it adjusts to what's in the window. You can dig into the weather information that we have here, the rainfall, temperature, growing degree days for the years that you select and the units that you want. Yeah, you can fill in the states that you want to look at, the previous crop that you want to subset the data by, and it just provides summary statistics on all of that information that you might want. And then we have, based on the nitrogen management decisions that you made, how was the cornstalk nitrate test levels coming back? Were they excessive, optimal, marginal, or deficient? And so, yeah, it's just some nice summaries of, oh, we're following these practices. Let's see how other people who follow the similar practices end up. Yeah. This is a cornstalk nitrate test. So what you do is it's a destructive end of the season test where you cut about 12 inches off of the bottom of the cornstalk. Yes, yeah. Okay, so that's a previous project. We'll get to some stuff I'm currently working on at the end, but so this is the outline of the main focus of the presentation today on this experiment where we're testing the effect of dropping the control treatment. So I'll cover some brief background information. I'll kind of break down the analysis that I did, go through some specific sites as examples, then we'll see how those results generalized for all of the data, and then draw some conclusions from it as well. So as a group of soil fertility people probably know, fertilizer rate trials are normally done on a small plot, kind of design multiple reps, a variety of rates. Here the data we're working with has 8 rates from 0 to 315 kilograms per hectare. And then you go ahead and you fit your model of choice, or whichever one fits the best. And then you calculate an AONR, which is the rate, the optimal agronomic rate, the rate beyond which we don't expect to see an increase in yield. For here on out, we'll call that XS, and it's a function of a couple parameters from the quadratic plateau model. And then there's some uncertainty associated with that estimate. And because it's a nonlinear model, you kind of have to estimate that uncertainty. And so we did that with the delta method, which basically treats the nonlinear model. It estimates it as if it were a linear model, and that's good enough. The red bars going out from the AONR are 95% confidence intervals. Yeah, we can have a discussion on model selection at the end, but what we did was we basically had this data set that had already been analyzed. They used the quadratic plateau model, and so we just did what they did. Got the same results, and then we did our analysis on top of it. So when we switch from research plots to on-farm trials, there's a lot of things that change, some assumptions and design choices that need to be considered. Generally, there are fewer nitrogen rates, so you'll see maybe 4, maybe 6 rates as opposed to the 8 that we have. The ranges are much narrower. They might be from 150 to 280 or 300 kilograms of nitrogen per hectare. A lot of them will exclude control treatment, that N0 treatment. Farmers don't like doing it. They don't like how it looks. They get yellow spots in their field like we're seeing in the image here. It loses them money, and they think, well, I know my optimal rate isn't 0, so why am I applying 0? So they don't like it. And we have less control over the design when we give it to the farmers and say, follow these general rules and just do everything else you normally do. I was looking over previous presentations in the seminar series, and some advice was given that you should probably be there when treatments are applied. Because from what I've heard, like farmers will say, well, I know it said apply 0, but like you didn't actually mean 0, right? So I did a little bit. We mean 0, and you need it to be 0 if you're gonna accurately analyze your data anyway. So getting everybody on board with the protocol and being held accountable and being there when the treatments are applied, all good ideas. All right, so I kind of mentioned the differences between research plot and our on-farm trials. Now I'm going to show a few examples. Hopefully not identifiable. I'm not trying to call anybody out, but they're just popular examples of some on-farm trials experiments, how they're being done. And the goal for these is to optimize nitrogen fertilizer use. So this is one example. They separated their fields into low response and high response and fit those differently. And the nitrogen rates go from 79 to 129. So that's kind of that narrower range that I was talking about before. Another example here of a field, again, with the range of rates from 187 to 292. Again, not using a control treatment. Here's another example of a paper where they do actually have a 0 rate, but their criticism was, well, there's a lot of bias in the EONR, the EOR as they call it in this example. It's very dependent on the model that you choose. And it turns out you can get them to all agree with each other if you only consider a few rates, which, if you didn't know, you can get them all to agree perfectly if you just do one rate. But the error term is, going from 7 or 8 rates to 3, your uncertainty is huge. So I wouldn't do it this way, but I'll explain. I'll get to why. It's not just my opinion. All right, so the type of analysis that we did is a leave one rate out analysis. So we take a normal field that we already fit to our model. We drop 1 rate. Here we drop the 0 rate. You fit the quadratic plateau model. You calculate the AONR missing the N0 rate. You calculate the standard error. And then you put it back in. You take out the next rate. Do it all over again. Put it back for all of the combinations, so that we can then compare, because we're interested in what happens when you leave out the control. But in order to know, we need to also leave out all the other rates and then compare what happens when we left that rate out versus another one versus another one. I'm not sure how many of you are familiar with an image that looks like this. I might as well get it tattooed on myself at some point with how much I end up talking about it. But it's the difference between accuracy and precision. And let me get rid of this bar here. There we go. Okay, so the ideal scenario is what we see in the bottom right, where we have high accuracy and high precision. So the points are all close together and they're at the center. That's obviously the ideal scenario. Now in the top right example where we have low accuracy but high precision, there's bias. They're all missing in the same direction, but they're still close together. That can be corrected for, I would say that's maybe your next best option. You just subtract the bias from everything and you end up in the center. The bottom left, we have high accuracy and low precision. So we're centered around the middle of the target, but we just have a bigger spread than we do in the ideal scenario. And worst case, you don't have anything and it's just a cloud of points all over the place. And so that's the scenario we're trying to avoid. And hopefully with what we talk about today, we'll avoid that scenario moving forward. Now, so that's conceptually what these things are. Numbers, how do we actually quantify these things? Because I'm not going to show you a bunch of targets today. Okay, so we calculate bias generally as whatever our estimate is from the true value. We quantify it here because we don't know the true value. We just say the value we get when we include all of the data. That's the true value. And then our estimate is when we're missing one of those values. So we calculate this for every single field and for every single subset where we're excluding one of the rates. So that's what the I and the J subscripts are for. 8J is when you're using all 8 rates at field J. And then for precision, we calculate that by a percentage change. The formulas are the same, the top and the bottom. It's just the top one is a little bit easier conceptually. The bottom one is easier mathematically. But we're basically assuming, okay, we know there's uncertainty at every field when we use all 8 rates. What we're interested in how much does that standard error change? And so that's why we're calculating the percent change in standard error. So we've got the standard error of some rate when it's missing rate I at field J, subtracting that from the AONR using all 8 rates for that field, dividing by the standard error of the AONR of all 8 rates. Yeah, hopefully that's clear. Okay, and then, as I mentioned before, the research question is what happens to the bias and the precision of the AONR when we leave out each nitrogen fertilizer rate from the trials? It's Friday afternoon. I get it. I usually have a 2-hour stats class at this time. So hopefully to keep you guys alert, engaged, paying attention. I've got a few potential scenarios and you can pick your favorite one and we'll see who's right at the end. I won't make anyone raise their hand on which one they picked because I wouldn't want to do that. All right, so scenario number 1, let's say that this N0 rate has a disproportionate impact relative to the other rates on the bias and the precision. Maybe it's less important. Maybe like those farmers think, oh, it's way on the end. You know, I know it's not close to my AONR. We don't need it. Let's leave it out. You could think that all rates are equally important. You know, maybe scientists don't have a favorite, parents don't have a favorite. So I'm told. Or maybe leaving out the rate that's closest to the estimate has the greatest impact. Maybe you think, okay, our AONR is 200. And so if we leave out the 200 rate, that's going to really harm my experiment. So the closest I can get to having a treatment that's right next to my estimate, that's going to be the best one. So pick your favorite and we'll discuss it as we go. So the experiment or the data set that we're looking at here was a collaborative process over a few years from a bunch of different universities in Corteva. I have the citation provided here, but there's 8 treatment numbers. The nitrogen applied at planting goes from 0 to 315 at increments of 45. Ammonium nitrate was the source for all of the for all of these treatments. And there was some cleaning steps that we took to get from the complete data set to what we have, but we went from 49 sites to 38. Okay, so now I'm going to go through a few specific examples to kind of illustrate different outcomes that we observed, and then we'll generalize them to see how common each one was. So we have one example of positive bias. This is from site year 8, where when we use a complete data set, we get that red triangle AONR of 125. And then when we leave out the points at the 0, then we fit that blue dotted line, which gives us an AONR of 176. So we see here, if we exclude the control treatment, we're going to be overestimating the AONR by 51 kilograms. That's a pretty big economic loss. Additionally, the change in standard error goes from 11 to 30. And so that's an increase of 155%. So that matters quite a bit when you think about how wide that 95% confidence interval gets. So that's an example of positive bias. Now we've got an example of negative bias. This is a different site. But when we analyze with a complete data set, we get an AONR of 133. When we exclude the control treatment, we get an AONR of 98. So then if you leave out your control treatment, did everything the same, it would tell you to apply 98 when you should be applying 133. And so that's, losses out that you're leaving out in the field there. Additionally, the standard error goes from 20 to 36, so that's an increase of 70%. And then we did have a few sites as well that had a near zero bias. This site here had an exactly zero bias where the AONR was the same whether the control treatment was included or not. However, the standard error increased from 29 to 50, so that was an increase of 70%. So maybe you're catching on to a little bit of a theme here, but we'll get more specific as we go. So those are some specific sites and what they were doing. So let's generalize it to all the sites that we had in our data set. So here, again, the reference is the complete data set, and then the other ones are the dropped treatments. The red dots are the means, and the orange line going across is just an extension of the complete mean, just for easier comparison as you get further away from the treatment all the way on the left. So as we can see, they're all pretty close. There's really no systemic positive bias or negative bias. They're not too bad, and statistically none of these are significantly different. However, when we get to the precision, now we start seeing some interesting significant results. So again, we're comparing these from when we used the whole data set, so that's why there's no complete box plot here. It would just be a straight line at 0. But we can see very clearly that excluding the control treatment led to, on average, a change in an increase of standard error of 40%. A lot of the other, so if you chose your potential outcome at the beginning, hypothesis 1 was the correct one. And interestingly, so we saw that the AONR average was about 200. And if you look at the treatments around 200, that 180 and the 225, those actually saw the least impact when those rates were excluded. So possibly counterintuitive finding, but definitely interesting and definitely something to consider as you're designing your own experiments or consulting on people who are designing experiments. So we had these great results. We brought them to one of our co-authors, and he said, okay, that's great, but can we predict the individual bias at each site? Which is a very interesting question. And so because if you can predict the bias you're going to have, maybe you don't need the control treatment if you can just estimate it based on some other parameter. And so we hypothesized, we have a bunch of soil data that they collected, a very extensive data set. And so we, conceptualize, well, maybe the organic matter has something to do with it, because if we have high organic matter, then maybe the sites are doing really well when we leave out the control treatment, and that's going to bias the results some way. Water content and sand were also some parameters that seem to have some promise based on some initial analysis. And then also the question of, well, how do we analyze the soils, because they were separated out by horizon, and the depth of each horizon was recorded and not the same. And so we were thinking, okay, well, do I analyze them just the O horizon, the O and the A horizon, the O, the A and the B horizon, the E horizon? Do we combine them? Do we just go to 15 centimeters, 30 centimeters? Maybe the states, one state is biased over another one, maybe 1 year's more than another one. Long story short, no, we could not predict the bias. The closest we got was an R-squared value of 0.44, which is not enough to provide you any certainty that you can exclude it and make up for dropping the control treatment with some soil parameter. But an important finding nonetheless, because again, it just highlights the importance of that control treatment. So in conclusion, excluding our control treatment did lead to less precise estimates of the AONR. It is also more impactful with fewer rates. So one thing that I did, that was Edger's idea, was, well, because there's kind of, I just thought intuitively, well, if we have 8 rates and you drop 1 and it has an impact of 40%, if you have 5 rates and you drop 1, that's gonna matter more. And it increased the standard error by 120% on average when I simulated data and just used 5 rates. And those 5 rates might be, it's kind of the bare minimum, but it does cover like your 0, your low, recommended, high, and then excessive rates. Also, when we only have 5 rates and we drop a controlled treatment, what you're really left with is kind of just a cloud of points. And you're going to have a lot of model convergence problems if you don't have that anchor point down low to fit your quadratic plateau model, because the model's not going to know that it reached a plateau. And if it doesn't reach the plateau, it can't converge the model. And so we saw about a 40% convergence failure rate when we only had 5 rates and dropped a controlled treatment. So if you want to fit a model to your data and you want the work that you did and the design that was executed to matter, you want to minimize your convergence issues as much as possible. And when we included the controlled treatment with 8 rates, we only had like a 3% convergence failure rate. And so my question to you is, what would you give to reduce your error if you could reduce your error by 40%? We have people that are collecting weather data. We have people collecting soil data, management data, history of the site, all trying to pick apart differences and distribute error. And this seems like some really low-hanging fruit, that if you just include this one treatment, then you can avoid some of those issues later on in making the extra steps that you're taking more impactful. And so then, catchy conclusion that goes with the catchy title: if you lose the control treatment, you lose the control of your estimate. So that's the big main finding of this study. Some other stuff that we're working on is identifying some covariates in nonlinear models when we're using absolute yield versus relative yield. Statistically and mathematically, there's some issues when you do the calculation to convert to relative yield. Number one, you can't do an economic analysis with relative yield, because if you increase your yield by 5%, the amount of money you make depends on how much that 5% is. And so you have to convert back to absolute yield anyway. The maximum yield, that 100% that you're converting all of your other yields to, is also poorly defined. There's a bunch of different calculations that can be done to calculate it, and depending on the one you use, it's going to change your results. And if you're aggregating over multiple studies that used different calculations for the maximum yield, those can't be compared evenly. So it introduces some bias in the calculations that way. But what we were interested in was, can we identify a nonlinear covariate? So relative yield can only capture proportional effects. And so we hypothesized, this is all simulated data, so we hypothesized a scenario where we have low yields when there's very little rainfall. And then if you apply fertilizer, so like site year A on the bottom, that red line would be an example, where we have really low rates, we don't have a lot of rain, you apply fertilizer, it maybe helps a little bit, but the more fertilizer you apply isn't going to do anything because you're limited by rainfall. And then as you get more rainfall, maybe you're seeing higher yields with no fertilizer, but then when you do apply fertilizer, you're seeing a bigger impact over greater rates, and you maybe get a scenario like we see on the left. And then when you translate that to relative yield, it turns into something on the right. And so when you look at the relationship that we created, so this is, again, all hypothetical, there's a relationship between the rainfall, our covariate of interest, and the parameters in our model, the intercept, the breakpoint, and the slope. And what we were really interested in was the breakpoint here. And I made it nice and easy, just a straight line, perfectly correlated. And then I said, okay, here's the data, they're perfectly correlated. I introduced noise and I said, can you identify the covariate that this relationship that exists because I created it to exist? And we were 20% more likely to identify the correlation when we used absolute yield as opposed to relative yield. So I think that's, useful. There are people that prefer to use relative yield over absolute yield. I understand why, and I understand why we do it, and especially why we used to do it. But I think the ceiling on the progress that we can make with relative yield is lower than the ceiling if we use absolute yield, where maybe we can figure out, well, why do we have these different yield responses in these different sites? Maybe there's different soils, maybe they experience different climate conditions, maybe there was some different management conditions. All of these things that we're just we could be completely breaking that relationship when we're converting to relative yield, that we can make up for with absolute yield, despite it being a little bit, a little more complicated right now, because some relative yield site data does look really nice and neat and can make some nice relationships. But I think as we can start attributing certain responses to what's out in the field, that will improve our recommendation. So I think the ceiling is higher if we use absolute yield. And then another thing that we've started working on is this quadratic plateau quadratic model. Now, the reason why we thought this might be something worth considering is because we saw sites that looked like this. And this is with the quadratic plateau model. If it's okay, but at the highest rates, it kind of looks like it might be dropping off. So maybe we're reaching a level of toxicity. In the plants here, they're not yielding quite as well as you over apply nitrogen. And so with our quadratic plateau quadratic model, don't blink, it's pretty similar, but you get something that looks like this. Now this, so we did have some sites where this model did fit better than the quadratic plateau model. So I'll just kind of show you what the quadratic plateau quadratic model looks like. It's really ugly, but it makes the calculations easier, and we'll break it down a little bit. So this is what the equation looks like. It's pretty gross. But if you break down the A and then the bx and the x squared components, it kind of just looks like a quadratic model. So like I have shown in the red box on the bottom. So A, again, is just the intercept, it's the yield with no fertilizer. The B term is the slope. The XS is the first breakpoint. So that would be like what we've been talking about with the quadratic plateau. And then the DXS is the second breakpoint where we start to see the decrease. And one of the things that gives this model a little bit of extra power is that it's symmetric. So the quadratic function that is on its way up is symmetric to the one that's going down as well. And so that's what it looks like for one site, and this is what the horrible model looks like. This is what happens when you change one parameter at a time. So when we change just the A parameter, that changes the intercept, that shifts the whole thing up and down. When you change the slope, it changes the slope, and it changes where the plateau is as well. Changing the first breakpoint also changes how high the plateau is, of course, and then changing the second breakpoint just changes where it begins to decline. So some of the questions that we're thinking about in regard to this model is what can it be useful for? Because if we're going to use it for nitrogen recommendations or any fertilizer recommendation, we have to make sure that we're getting to that really high rate and we're starting to see a decrease. So it might be useful for some nutrients. It might also be useful for data over time, maybe like photoperiod or LAI, something like that. So we're kind of just running through a whole bunch of different data sets that we can get our hands on and seeing if they'll fit and maybe what characteristics the data sets have that do fit. I think, again, that this quadratic plateau quadratic model will also perform much better with the control treatment. So just bringing it back to the main point of the point of this talk was that if you lose the control treatment, you'll lose control of your estimate. With that, I'd like to thank you all for your time. I'd like to acknowledge my lab mates and our support systems here. Their feedback, their ideas have been very helpful to me. Hopefully I'm helpful to them as well. They help me think differently. Some of our projects are a little bit related, so we can kind of think about how our ideas are working together. And yeah, so there's my contact information. If you want to reach out and talk more about it, I would be more than happy to do so. And thank you again. And I'll take any questions that you guys may have. Yeah.
So question is, you've done an extensive literature search on this, obviously, as part of this process. How many nutrient studies are done without the control, without the zero? Percentage wise, is it half? Is it a third?
I would say for the on-farm trials, it's definitely more common. It may be somewhere around a half or a third from what I've seen. Yes, for on-farm research. And another thing that I'll mention about this and kind of the unique approach of going to a fundamental experimental design is that this can be generalized to any nutrient, any crop, any state. So hopefully it's beneficial to people here in Florida as well.
So maybe a follow-up question to that. So if I understood what you were presenting, where the error increases dramatically, does that mean that without the control on farm, probably they're not detecting differences where they might otherwise if they had a control?
Differences between trees. Yes. Mm-hmm. Yeah. Yeah. And a lot of the studies that I see of on-farm research, and especially with AONR or EONR, is they only give you the number. They don't give confidence intervals. You have to estimate them, and so maybe you only can apply one rate on your farm anyway. But you want to be confident in the number that you have. If you're stepping on a scale, you want to be confident that the number that it says is accurate. It's a similar concept here. I would also like to point out too, now that I'm thinking about it, so we used AONR for everything here. The results apply exactly as much to EONR, the economic optimum, because the EONR is just the AONR curve minus a straight line. So it's with no uncertainty. So the results are going to be exactly the same if we were to convert to EONR, but in order to avoid including the costs in your yield and in the fertilizer, we just left it out because it doesn't make a difference. Yeah.
There is a scenario often observed in vegetable research. They include a zero rate because they want to calculate nitrogen use efficiency. Need that zero rate. But then they have three rates. The one that they peg as the optimum rate, and then bracket on either side of it. Based on your presentation, if I interpret this correctly, that's really not a good idea. Am I right? That assessment or not?
Yes, I think it depends on how confident you are in the response. If you think that it's a linear response, then applying it zero, applying it at the rate that you expect is the optimum are the only rates you need. But we have so much uncertainty, and maybe you don't know if it's a quadratic relationship, or you don't know different things like that. So from a statistical perspective, it's better to have them evenly spaced out between your minimum and between zero and your maximum rate.
Yeah, in this case, what you see, you have zero rate, and the first rate is close to 200 pounds per acre.
Okay.
And then you go up from there.
Yeah, yes, I was wondering about how far out those brackets go. Because if it's narrow, they're, as we saw here, they're not really providing much information on what the optimal rate is. You're much better off, again, evenly spacing them out.
And that brings up the question, if you have limited resources, and what can you do in terms of the rate by perhaps dropping a replicate or two?
I definitely, so I looked over the previous presentation slides, and I agree with you that if you are including more reps, you're not getting nearly as much as you are if you were to sacrifice your fifth rep for another rate. I think once you get past 3, maybe 4 reps, you're really not getting anything beyond that. So I'd be, and my advice actually has a paper on that exact trade-off between the number of rates and the number of reps. And beyond 3, you're really not getting much. You'd be much better off adding rates than reps.
But we are operating under a scenario that a standard agronomic or horticultural experiment has to have 4 reps. I mean, I don't buy it, but what's your assessment? I mean, you're saying the trade-off is when you go beyond 4, but 4 is the maximum number.
Okay, then yeah, I would say 3 is sufficient. I'd say probably 2. I mean, it depends on if you have 8 rates and 2 reps, you're also adding, if you add a third rep, that's 8 more plots as opposed to 2 more if you have 2 reps and you're applying 1 more rate, then you're only applying 2. I think part of it too is not even from a statistical perspective, but what happens if a deer comes in and destroys this plot? What happens if we lose some data for some reason or another, or we've got some outlier? So that needs to be built into, like, that's an important part of why we have replicates as well. But I think and I don't think there's like a magic number, but I would say beyond 3 reps, you're probably overdoing it.
Yeah, and I believe it needs a change in mindset. We are not talking about treatment differences. We are talking about defining the overall response, and we are defining the estimate of the change in yield relative to, in relation to a unit change in what we applied. So we're not estimating treatment 1 versus treatment 2 and so on, but it's the over curve. And I believe that's going to give you the power.
Yeah, absolutely. Chat is disabled. All right. Yep, Simon, do you have a sense of whether and to what extent other models may be more or less sensitive to removing the control? Is there a more robust model available, known or suspected, or your hunch? That's a really good question. I appreciate you bringing it up, Simon. This is something I've thought about quite a bit. And I think the quadratic plateau model, the one that we used, is probably one of the more sensitive ones. I think if you have a linear plateau model, it's going to be less impactful to leave out the control treatment. I haven't done it, but I would suspect that to be the case. A quadratic function, again, the wider your range of treatments, the better off you're going to be. So by leaving off a control treatment, you're shrinking the range of the quadratic model. So I think it's still important to include it then. Will it have as much of an impact on the optimum as compared to the quadratic plateau? I suspect not as much, but that's not to say none at all, for sure.
Now, if you have a problem, you mentioned the convergence problem with a quadratic plateau model.
Yes.
What would happen if you just strictly went to a quadratic model, doing that and taking out and then you would be, of course, you would be in a linear situation because it's a quadratic equation, so it's a straight linear, and that shouldn't have any convergence problem.
Yeah. I mean,
my approach is always if you have to choose between a more complicatedness that doesn't converge and a simpler model that converges, choose a simpler model.
Yeah, absolutely.
Because in the end, as a famous statistician once said, all models are wrong. Someone used.
Right, exactly. Yeah, I agree. Getting something simple that converges is better than getting something complicated that doesn't. Yeah.
So I have a question. So in the summary, you said, what would be the minimum number of rates for an on-farm trial? A control and 4 rates, or control and 5 rates?
Minimum, I would say a control and 4 rates. And again, you want to make sure that that highest rate, that excessive rate, is excessive. Because especially if you're fitting a quadratic plateau model, like, because that's true for every model that you fit, but if you're doing a quadratic plateau, you especially need to make sure you got to the plateau. And so by having that really high rate, that will help with those issues. It also depends on how complicated the model is that you're fitting. If you have a quadratic model, from a statistical perspective, the optimal design to reduce the error is the 0, the highest, and in the middle. And so if you know it's a quadratic relationship, that's what you'd want to do. If it's more complicated than that, then you definitely want to evenly space out more rates. So I think personally, like just as a general rule, I think having at least 5, that 0, low, optimum, excessive, very excessive, is the bare minimum for sure.
So, and as opposed to spacing them evenly, and this is a follow-up on the earlier question, having a control, maybe guess the optimum rate, peg it, and then have one excessive rate, would it be equal to having them evenly spaced?
Statistically, that would not have the power as if they were evenly spaced out. So when we, I can go back in my slides here to put you guys out of the way. These here would be kind of like a scenario in my mind where, okay, let's, because we did have the optimal rate of like 200 from this graph here. So that would be a scenario where we've got a rate here, we've got a rate here, we've got a rate here. And they're really not doing much to reduce the standard error from our model.
Just a follow-up comment, if I may. this works beautifully for nitrogen. Because once nitrogen enters the soil, there's not much happening. You either have ammonia or nitrate. But this does not apply to other fertilizers like P, for example. You put P in the ground and a lot of chemical reactions start happening.
Mhm.
And so as long as we limit ourselves to, yeah, this works for nitrogen, fine, it's important. But it would be dangerous to extend, we still need the rates, but in generally what we've seen here is that with phosphorus fertilization, we see no matter what the background level is, we see a linear response. We
Okay.
can't get high enough to get any kind of a plateau model.
Hmm. Yeah, and I think that, you know, this to go along with what you're saying is this requires, you know, knowledge provided by the researcher to inform the experimental design. It's not saying use this experimental design all the time, ignore everything else you already know. Just integrating into it. Yeah.
In the end, we are all Bayesians.
Yes, yes.
And I would have another follow-up that just came to my mind. You know, when you had your plateau quadratic model, and you mentioned increasing the nitrogen rates, I remember an example I used to use for teaching from Overton, Texas, where they did a forage study and they went to something crazy like 800 pounds of nitrogen. Was, you know, was hugely excessive. Their conclusion was they started seeing a decrease, that the yield was actually limited by availability of other nutrients at those huge rates.
Mhm.
So when you mentioned maybe toxicity, it actually may not.
Okay, more of a competition
More
mechanism.
of a, you know, I have enough nitrogen, but now I'm running out of zinc, you
Mhm.
know, of bioavailable zinc or something like that,
Mm.
rather than, hey, it's getting toxic, you know.
Sure. Yeah. Point well taken.
Any more questions? In the audience, do we have any more? And off topic, we have got one.
Where did you get your ammonium nitrogen fertilizer? So that was done by the original authors. They each individual site, it was up to them to get it for themselves. They didn't have one source of ammonium nitrogen that they then sent out to all the different states and all the different sites. They left it up to the farmers to like, hey, go get it where you normally get it, but just get ammonium nitrate and get these rates.
Did they actually test the content
I'm not sure.
in the original study?
I'm not sure.
Because I have no feel for it, what natural variability would go in the formulation process.
Yeah, I'm not sure. The percentage is like 34.00, but I don't know. Is it always 34? Is it sometimes 33 or 37 or 40?
Yeah, I've seen values ranging from 30 to 3400.
Okay. So maybe that could be another, you know, source of variability.
Well, if not, thank you.
Thank you.
And out in Zoom land, if you're still around, we'll see you in the first Friday in December. Dr. Hans-Peter Piefel from Hohenheim University in Germany is going to talk about designing, using a Bayesian approach to design fertilizer rate studies or end rate studies, to be specific. You all have a good weekend.